calculate the derivative of it, whatever it is, and say that that derivative is negative. So I'm calculating the derivative of this, and I'm saying that this is negative. So what does this mean? The slopes, the change in slope is negative. So that means that slopes are decreasing actually. And hence I can say f double prime of x is negative. So if I summarize this, what do you call the concavity test? Let's call this, what do you call concavity test. Concavity test. So the concavity test. Okay, so I just don't want to introduce test as a fact actually. So I want to give you an intuition actually that why the test the way it is. We can have it, we had an intuition for first derivative, it makes perfect sense. Now we saw that okay, when the prime of the prime is positive, that means that the prime is increasing, or the second prime is positive. And when the prime of the prime is negative, that means that this is decreasing. In other words, the derivative of the derivative is the second order derivative actually. Okay? So here is this. So you're going to say that, okay, if f double prime of x is positive for all, say, x in an interval I, then the graph is concave up of f is concave up actually. And then if you say that if f double prime of x is negative, then for all x in I, then the graph is concave down in the interval I actually. Okay, in the interval I. So this is concavity test. You want to know whether in a given interval function has a function is has a graph that is concave up or concave down. Just check what is the sign of the second order derivative in that interval. If it is positive, you are talking about a concave up curve. If it is negative, you are talking about a concave down curve actually. Okay? And here is the thing. If your curve is concave up, that means you must have a minimum. So, in a concave up curve, if you have a critical point, then that critical point must be minimum. Must be minimum. And if you have a concave down curve, and on that curve you have a critical point, then that critical point must be maximum. So, in other words, concavity also tells you an interesting criteria to know that whether a critical point is maximum or minimum. Okay? And this is called second derivative test. Second derivative test. Much more easier than first derivative test to apply actually. But every test has its own benefit. This stuff would be very important when you want to make sense of the curve actually. Okay. So here is what do you call the second derivative test. This is called the second derivative test. So in order to apply the second derivative test, first you have to find the critical points. So you're going to say suppose C is a critical point of f. That is the derivative of f prime of c is 0. Then if number 1 at this critical point second order derivative is positive. Okay? Second order derivative is positive. Okay, second order derivative is positive. So you're going to say, then this x equal to c is a minimum. And second, if f double prime of c is negative, then x equal to c is a maximum. Okay, this is what we call the second order derivative test. Because if f double prime of c is positive, that means that you have this concavity up concavity, so you're going to have a minimum point. And if f double prime of c is positive, you're going to say that you are talking about a concave down curve, so the critical point must be the maximum point actually. Okay? So I hope this is making sense to you. So we had two tests actually. So one way to determine what is a maximum minimum is first derivative test. First derivative test is simple. It says that see the slope of the tangent line before the point and after the point actually. So if before the point if it is negative and after the point it is positive, so it's minimum. And if this is a critical point, before that the slope of the tangent line are positive and after the tangent line are negative, then this is the maximum. But there is another way, what you call the second order derivative test, an interesting way, that if f double prime of c is positive, then x equal to c is minimum, because we are talking about a concave up curve. And if f double prime of c is negative, then your x equal to c must be maximum, because you are sitting on a concave up curve actually. So concavity also play an important role in finding what is called the second order derivative. So let's do two things. Number one, let's apply second order derivative test to a function and try to make the graph of the function using the concavity test and the second order derivative test actually. Okay? So let's do this example. So what should be the first step? The first step should be find the critical points and then see that where the function is concave up and where the concave is down. And then check the sign of the critical point, check the sign of the second order derivative at the critical point and see whether it is positive or negative, then it tells you maximum and minimum. So let's start with, let's take same function example. So let's take same function, f of x equal to, what do you call, x power 4 minus 4x cubed. So the f prime of x is going to be 4x cubed minus 12x squared. And f double prime of x is going to be 12x squared minus 24x actually. Okay. Now how to find the critical points? To find the critical points, we'll take f prime of x and equate it to 0 and solve the equation. So when you have 4x cubed minus 12x square equal to 0. So we took 4x square outside, and I have x minus 3 equal to 0. So this means that x is 0 and x equal to 3 are the critical points. Okay? Now, out of these critical points, which critical point is maximum and which critical point is minimum? Now, if you compute second order derivative and substitute it, for example, the first critical point, f double prime of 0, here is something very interesting that you get actually. So f double prime of 0 is going to be 12 times 0 square minus 24 times 0 equal to 0. In the test, we talked about when f double prime of c is positive. We talked about when the f double prime of c is negative, but we didn't talk about when the f double prime of c is 0 actually. Because when the f double prime of c is 0, you're gonna say, aha, this is a kind of a place where the function is not changing its behavior actually. So it's neither maximum nor minimum. So x equal to 0 is neither max nor minimum. You know, you call such points as the point of inflection. I told you actually. How about x equal to 3? So you see, second order derivative test is very simple to apply. Now take the second critical point and substitute it into, what do you call, second order derivative. F double prime of 3, so you're going to say this is 12 times 3 square minus 24 times 3 actually. Okay? So whatever this number is going to be a negative number actually, I think, yes. So it's going to be a negative number. What would be the number? So it's a 36 actually, so it's a positive number. And since the second order derivative of at 3 is positive, so you're going to say the x equal to 3 is minimum. Okay? So the function has only one local minimum actually. Okay? Maybe that local minimum is also an absolute minimum. The second order derivative test is simple to apply. Now I want to do what? The next thing that I would like to do, I would like to make a sketch of this curve actually. And if you want to make the sketch of this curve, you have to check for the concavity. Where? So here is the thing actually. Take your critical points. So where are your critical points? So the one critical point is this, x equal to 0. And say one other critical point is this actually. So let's call it x equal to 3. So this is 3 and this is 0 actually. So on this white line, if you put the two yellow lines, then this is going to split this real line into 3 parts. So one part is this, okay, and the other part is this interval, and the third part is, for example, this interval. Now on each of the intervals, in order to make a sketch of the curve, on each interval, in other words, on blue interval, pink interval and yellow interval, try to find the concavity of the function actually. Okay, this is what that we like to do. So what do we like to do? We like to do that, try to find the concavity of the function. So in order to find the concavity of the function, you need to do what? You need to check the sign of f double prime of x actually. Now what is f double prime of x? We already know it. Okay? We already know it. that f double prime of x is really, if I write it more explicitly, it's going to be 12x times x minus 2 actually. So this is what it is actually. Okay, this is what it is. Now, the positivity or the negativity of the f double prime of x depends on the sign of x and x minus 2. So for example, if x is positive, x minus 2 is negative, then the product is negative, and hence f double prime of x is negative. If the both are negative, then the product is positive, and hence the function would be increasing. If the both are positive, the function would be increasing. Then f double prime of x will be positive as well. So again, we will make what you call the table. Okay. So here I'm gonna put interval. Which interval? These intervals, blue, yellow. So the one is minus infinity to 0. The other is 0 to 3, and the other is, what do you call, 3 to positive infinity. Okay, this is what are the intervals. And then put these two factors, so x minus 2, and let's put f double prime of x. And here, in the next column, let's put concavity. Concavity. Now, if you choose a point from this interval, so you can choose many points. For example, let's choose, say I'm choosing minus 1. Okay, so let's take minus 1. So if I substitute minus 1 into x, I'm going to get a negative number. If I'm going to substitute minus 1 here, I'm going to get what you call again a negative number. Minus 1 minus 2 is going to be minus 3. And then the product of these two should be positive. Okay, the product of these two should be positive then. It's not necessary that you should pick one point. You can pick another point. For example, instead of taking x equal to minus 1, say you substitute minus 3 actually. So if you're going to substitute minus 3 in x, you're going to have a negative number. Minus 3 minus 2 is still negative. So this is true. So make sure that whatever conclusion you are making is true in the interval actually. Okay? Now tell me, what is the meaning of having a positive sign in what do you call this interval? Positive sign of f double prime of x in this interval. So you're going to say the curve is concave up actually. Okay, the curve is concave. The curve is concave up. Why? Because the sign of f double prime of x in this entire interval is 0, no matter what value you take. How about in this interval 0 to 3? So for example, if I take 1, it should be 0 to 3 or 0 to 2. So silly me. Because, okay, I did one silly mistake. In order to determine that how the signs of f double prime of x are changing, I need to equate this to 0 and see that where these two numbers are, what do you call, when f double prime of x is 0. So f double prime of x is 0 at x equal to 0 and at x equal to 2. So we shouldn't take x equal to 3, but we should take x equal to 2 actually. This should be the case actually. So this interval should be 0 to 2. So you have to, so if you want to analyze f prime of x, then see that where f prime of x is 0, and then see what happens before that 0 and after that 0. So similarly, if you want to analyze f double prime of x, you need to equate that to 0, and the solution of these two is x equal to 0 and x equal to 2. and then see that what happens before x equal to 0, after x equal to 0, before x equal to 2, and after x equal to 2. So in other words, in this interval, let's now take, for example, any value between 0 to 2, okay, between 0 to 2. So let's take, for example, the middle value 1. So if I substitute 1 here, so this would be a positive number. If I substitute 1 here, this would be a negative number. So if you multiply both, you're going to get a negative number. So this means that in this interval, your curve is concave down. You can take another number. For example, you can choose 1/2, for example, between 0 to 2, or 3/2, 1.5, doesn't matter. So you're going to get 1/2 minus 2 is still going to be negative, 1/2 is going to be positive, so the concavity is down actually. How about 3 to plus infinity? So not 3 but 2 to plus infinity. Okay. So in the interval 2 to plus infinity, what is happening? Say take any value, for example, let's take 3. So if I substitute 3 here, I have positive number, and 3 minus 2 is still going to be positive, so the product of these two numbers is still going to be positive. So the curve is concave up again actually. Okay. So now what we are doing, we are trying to sketch the curve of f of x actually, f. So what we did, we computed the second order derivative, we saw where that second order derivative is 0. So second order derivative is 0 at x equal to 0 and x equal to 2, and then see that, then put these x equal to 0 and x equal to 2 on, for example, line, and convert them into the intervals, and then see that what happens in each of this subinterval to the f double prime of x. In other words, what is the sign of the f double prime of x in each of the interval? Okay, this is what that I would like to do. So let's now remove all unnecessary things, okay, and try to make a sketch of it. Try to make a sketch of it. So now, in the interval negative infinity to 0, the curve is concave up. And how does concave up look like? Something like that. So I'm going to say that now my curve is concave up, so it should look like something like this actually. So it's concave up actually. What is happening with the curve in 0 to 2 interval, so it's concave down. You have to keep in view that at x equal to 3, you also have a minimum actually. Okay, so it's concave down, and it goes to a minimum value. So imagine minimum value is this actually. So it is concave down, so it should be, if I still use blue, so it should be something like this actually. Okay, so it's a curve that is concave down. This is concave down, and the curve has a minimum at x equal to 3. Okay. By the way, you can also calculate this minimum, that if you take x equal to 3 and substitute it, it's going to be 3 power 4 minus 4x cubed, so you can really plot that curve as well. So I think x equal to 3 occurs at minus 27, so this point is really minus 27 actually. And then what happens to the curve in this third interval 3 to infinity? So you're going to say now the curve is concave up again actually. So how does it look like? So it is increasing in concave up manner actually. Okay, concave up. So if I make this curve smooth, the curve is really this concave down, and concave up, concave down, and then concave up again, and concave up. So this is really the sketch of the curve. That's how the curve should look like. Okay. So I hope it is making sense to you. So in this example, we did two things. Number one, how to find the maximum and minimum of the function. It's very easy. Just find the critical points and substitute those critical points into the second order derivative actually, and see that what happens, what is the sign of the second order derivative at that point. So if it is positive, your point is minimum. If it is negative, your point is maximum. If you want to sketch the curve of curve using what you call the concavity test, then you have to do what? Calculate your second order derivative, equate it to 0 and find those zeros, and then split your x-axis by into the intervals actually. For example, I put a line x equal to 0 and I put a line x equal to 2 actually. So when I put these lines, I got 3 intervals. One less than 0, other 0 between 0 3, and other 3 to infinity. And then in each interval try to find the concavity of the curve. So what I did, in each interval I saw that okay, in this interval what is f double prime of x? So it's concave up, concave down, and then up actually. And then just make a graph out of it. So we made a graph. Okay, we got it again. So you can see that all this stuff helps you to do a lot of things, including the curve sketching actually. Okay. This is it for so in this part we kind of covered what do you call a mean value theorem. Just have an intuition of it, and then we talked about first derivative test, second derivative test, when the function is increasing, when the function is decreasing, and then concavity test and second order derivative test actually. So we did this, and there will be several exercises based on it actually. Now I would like to move to a very interesting topic actually. So this is another application of, we'll do the practical applications in our next discussion, but in today's discussion I would like to talk about some of the applications that are really, within mathematics actually. So the next application of derivatives that we would like to do, that derivatives is an amazing thing that help you also to calculate what do you call some of the very difficult kind of limits actually. Okay. So you can calculate very interesting and difficult kind of the derivatives actually. Okay. So let's start with indeterminate forms actually. Indeterminate forms. I also encourage you to read the book. This is important actually. Okay, once you're going to read, you're going to make more sense actually. Okay. Now, think about these limits. Imagine you have this limit, and you have been set to compute limit what would be the limit of the function, say, log x divided by x minus 1 as x gets closer and closer to 0? By the way, what would be, say, another limit would be, what would be the limit, say, x equal to 0 when sine x over x actually? So what would be the limit in this case actually? So if you have a function sine x over x, limit x goes to 0.